Alright, let's make some rainbows. Red, orange, yellow, green, blue, indigo, and violet. The spectrum of visible light from the longest wavelengths and lowest frequencies on the left to the shortest wavelengths and highest frequencies on the right, at least on this diagram. Well, that might not be exactly the way the ancient Greeks would describe their messenger goddess Iris, but talking about frequencies and wavelengths, that's one way physics can talk about the rainbow. So let's make some rainbows, 3 of them, starting with the first and probably most familiar. But rainstorms, like goddesses, can be unpredictable, so we can get a similar result from a glass prism. The same colors in the same order, each deflected at slightly different angles. And this is the result of refraction, the change in direction of light as it enters a new medium and changes speed. The angle of refraction depends on the index of refraction and the angle of incidence. That's Snell's law. But the key to making a rainbow in a prism is that glass has a slightly different index of refraction for the different wavelengths of light. This turns refraction into dispersion. The same is true of water, and we also have reflection inside the water droplet, and that makes a rainbow. Reflection and refraction and different indices of refraction make a rainbow. See it for yourself. Just stand with your back to the sun. See the shadow of the tree. The back is to the sun is to the left. And then spray some water, spray some mist, and you will get a rainbow. Now, let's get another one. This time by looking through a slide with many slits or by wearing special glasses. This is diffraction, not refraction. This is diffraction, the spreading out of waves around a barrier. Diffraction, either from one slit or from 2 or from many, can result in a series of bright and dark bands, bright and dark lines, thanks to wave interference. Interference, the adding together of 2 waves. They can grow in amplitude, they can even cancel out. Finding out where the bright bands and the dark bands will be is then just a matter of counting wavelengths. Emphasis on wavelengths. The longer wavelength red light is diffracted to a greater angle than the shorter wavelength violet light. This means that white light, a mixture of all the colors, will be separated into a rainbow, which is what happens in a spectroscope, a simple device made of a tube and a diffraction grating with many slits. Use this spectroscope to look at an incandescent light or indirect sunlight, and you will get a continuous spectrum, a rainbow. But use the spectroscope to look at an energized gas like helium or neon, and you'll get a series of spectral lines, the color barcode or color fingerprint of the gas, each line corresponding to an electron transition. And notice here, if you were to add back together all those lines for helium, you get a slightly purpler net color, and if you were to add all the lines together for neon, it would be a little bit redder. But now, on to the third rainbow. This might be the most difficult. It's in a bubble. How did a rainbow get into the bubble or onto the CD or inside an oily puddle? To understand this, we'll need to return to our old friend, the index of refraction. But wait a second. How can light slow down? The wave's frequency needs to stay the same, but its wavelength can decrease, so keep that in mind. And consider color. How can a computer screen or a projector produce color? We get all the colors we can see from the 3 primary colors of light: red, green, and blue. Red and green together gives us yellow. Red and blue together gives us magenta. Green and blue light together gives us cyan. White light is a mixture of all 3 primary colors: red, green, and blue light. And we're talking about light here, not paint. And we're also talking not just about physics here, but about biology. You have 3 color sensing cones inside your eye, unless you're colorblind, and your color TV combines red light, green light, and blue light. Your color TV is really 3 different TVs in one, and the way it produces light, it produces those 3 colors, which is in concert with how your eye detects light, and therefore you can get a color television. And this also explains why magenta is not on the rainbow. That's interesting. I think that magenta is not on the rainbow. Magenta is what your brain calls the firing of red and blue cones together. Long wavelengths and short wavelengths together, without those in the middle, without green. If you add some green in, you'll get white light. Magenta not on the rainbow. Magenta in your eye when red and blue cones fire together. But if we can get it into your eyeball, how do we get it into the bubble? The answer: by shining light at it. Here, a ray of light is going through a layer of soap. It kind of zigs and zags just a little bit as it enters into that layer of soap. but we're more interested here in how the light can bounce off the clear soap. This is something you've seen before. Partial transmission and partial reflection in a window. Notice that, but here's the key. The reflection can occur. It does occur at both the outer and the inner surface of the bubble. Working out the details is a chore here because the angles change and also because the wavelengths change size inside the soapy water or inside the glass, and because the reflected amplitudes invert at surface A but not at surface B for complex reasons, but the result is two parallel rays coming off the bubble or off the glass, similar to the two waves we had coming out of that two-slit diffraction experiment. This is key because, like we said, two waves can interfere, they can cancel out, and that means we can get magenta in the bubble. That's where, see the magenta in the bubble? That's where the thickness of the soap layer is just right to cancel out the green light. So what do you get? You get red and blue together, you get magenta in a bubble, and there you are. 3 rainbows: refraction, dispersion, diffraction, color addition, color subtraction, rainbows. So thank you, Iris, for sharing with us some of your rainbows, these 3 rainbows, and thank you for showing us how they reveal some mathematical uniformities which are literally all around us, even if we often miss them.